Welcome to the second lecture of Mixed Signal IC Design course. In the last lecture, we had an introduction where we looked at the difference between an analog circuit, digital circuit, mixed signal circuit. We looked at, we understood what is a design, what is basically design with respect to this course, and what are the factors which determines final design. Now we also have reviewed the design trade of the octagon, what you already know from your fourth semester course. Then we also saw the importance of learning this course, even though the world is going digital. What is the importance of data acquisition and reconstruction circuits, right? Then, as we know, the two main things what we focus here are analog to digital converters and digital to analog converters. We looked at the input of an ADC as a CTCA signal, which is continuous in time and amplitude. And what we are expecting at the output is a discrete time and discrete amplitude signal. And also we concluded with the category of ADCs depending on the sampling. If the two types of ADCs we were talking about. One is Nyquist rate ADCs, another one is oversampling ADC. And with that, we'll start our course from today. And the first unit, as I mentioned, the first unit is all about sampling circuits, and we'll start by looking at sampling switches. So when we talk about sampling switches, I would like to categorize this under the heading of dynamic analog circuits. So let us try to understand what is a dynamic analog circuit first of all. So I'm sure that you would have heard about dynamic logics in your digital VLSI course, where especially when you studied about the various circuits like CMOS based circuits, the main category, one is static circuit, static CMOS logic, and another one is dynamic logic. So can I get your response here in the chat? What is your understanding of the static and dynamic CMOS logic CMOS circuits? Can I get few response here in the chat? Are you guys listening? Yes, yeah. Dynamic circuits, yes, they are clocked. They work at the edge of a clock, right? All right. Yeah, so that is the difference. So that is in digital circuits, whenever we say static and dynamic circuits work on clock. So there are various reasons why we go for dynamic circuits, and the important reason being or having a dynamic logic is basically for reducing power dissipation, and also thereby we can also reduce the number of devices what we use to perform any given operation, right? So that is why we go dynamic. I hope you will definitely recollect the advantage of dynamic logic over static logic, and one could be the reducing power dissipation, right? Now coming to our course in mixed signal IC design, where we talk about analog and digital circuits here. If you remember in your previous courses of AMC and AIC, we are talking about analog circuits, and we hardly use any clock based circuit, right? Now in this course we are actually starting with the clock based circuit, that is your dynamic analog circuit. Otherwise we call those circuits as sampling circuit. So the moment you hear the term as dynamic analog circuit, the one to understand it is these kind of circuits will exploit why we basically use these kind of dynamic circuit is actually to have or to store information on a capacitor, or store the information in the capacitor, I can say in the capacitor or in the gate capacitance of a MOSFET for some period of time. And that is basically controlled by a clock signal at the gate of the device. And the device, when I am referring at the device in this course, it is MOSFET, right? So in today's class, what we will do is we'll try to understand what is a basic sampling circuit, and how MOSFET act as a switch, and if I'm using MOSFET as a switch in a sampling circuit, what are the other details what I should know before I proceed with any architecture of ADC, right? This is today's class will be all about sampling switches. We may take 1 or 2 classes more in order to understand a little more depth in sampling circuit. We may we will look at in 2 categories. One is we'll look at the speed considerations, and also we look at the precision or accuracy considerations of a sampling circuit. Because the one picture what you should have in your mind is, first the very first block is this, and the sampling circuit is actually the signal or the output of the sampling circuit is actually being processed and converted that into a discrete amplitude signal, right? So we look both at speed as well as accuracy of the sampled output, what is available at the output of a sampling circuit, right? So to start with, as I mentioned, fundamental any dynamic circuit, talking about MOSFET switches. Our discussion is about MOSFET switch. So in another courses, we haven't looked in that detail about switches, because there we were operating MOSFET in saturation region, and we will be using for amplifiers. Now we need to operate this in switch, right? Now there are and when you say MOSFET switch, definitely from the previous course of digital VLSI, you may what are the different kind of switches coming to your mind when you hear MOSFET switch? Can I get some response here in the chat? The moment you hear a MOSFET based switch, it can be an NMOS based switch, where we will mark this as input, this as output, and this as the clock or the control signal. Similarly, you will have PMOS based switch. Again, this is operated with clock bar. I'm just drawing the reference as clock signal here. So this is your V in and this is your V out. And the third category is the combination of these two. So in the first classes, we'll try to understand why we need to go for a combination of this NMOS and PMOS, or why basically a transmission gate based switch is required. So this is V in and this is V out. And in that case, we'll write, if this is PMOS, we'll write this as clock bar and this as clock. All right, yeah. Maybe the screen where I'm seeing the responses, I'm getting delayed response. Ankit, I saw your response as pass transistor switch. Yes, so pass transistor, it could be either a N MOSFET, it could be a P MOSFET, or a modified version of having both the things in parallel, right? Now, so as I mentioned, when we talk about MOSFET, there are certain things specific to MOSFET. So one thing is, under DC conditions, we know that the gate of MOSFET does not draw any current, right? Because the gate is insulated from the rest of the device structure. So I can mention one thing about this MOSFET is, under DC conditions. Under DC conditions, the gate of MOSFET does not draw a current. That is in fact an advantage when we use MOSFET as switch. We'll see how it is. And also one more thing is, yeah, so this is one thing. Other thing is, whenever you apply a control signal to the gate of a MOSFET, that signal will not interfere with the information which is being passed through the switch. So what I meant is, so say for example, you have a switch here using a MOSFET, and you are controlling this switch using a signal at the gate. This is my control signal. But we know that this controls ideally, I'm telling ideally, because we look at some of the non-idealities where this control signal will have an effect on the output. But ideally, I can say this control signal will not interfere into the information which is being passed from here, because this is the input of the switch, this is the output of the switch. And normally, I can say this control signal will not have any effect, or control signal will not interfere with the information. That is one more point what we need to understand about this. So I can say the gate control signal So whenever I have a control signal at the gate, are you guys with me listening? Can I get your response in the chat? So gate control signal does not interfere with the information being passed. Right. But later we will see that there is an interference. We call that interference as clock feed through, because whenever you have a high frequency clock which is at the gate of a MOSFET, that will have some impact, and that impact is basically due to the structural capacitance in the MOSFET. We'll see that is actually, those things will be covered under precision considerations. Okay, so gate control signal does not interfere with the information being passed through the switch. So these are two good things about MOSFET. So that is why we generally, or even if you look at the modern devices, modern like gadgets, what we use for switches, we have like modified versions of MOSFET. So previously we had what I'm discussing is about a planar MOSFET, but now we have control over the channel in different means. Either it is through a FinFET or it is through a gate all around substrate. So different devices are available, and the main reason, or the fundamental structure remains the same, because a gate which is isolated from the rest of the structure. Right. Now, coming to the simplest sampling circuit. So because that is our interest here, probably you will recollect sampling circuit from your previous courses. So in very simple form, you can actually represent it as a switch. And so what I need is, I need to get the information at a specific instant, and I need to store it. So I can have two different options. Either you can actually use a switch with the capacitor to store the information, or you can use a switch and an inductor also. So in place of capacitor, this also can be used, but we generally will not use inductors for this, or at least for sampling, for the reason this will definitely draw a current, but in the case of capacitor, it is not like that. The charge is being stored and it will be available as a voltage across it, right? So if you have inductors, then you will have other complications in order to get the information and to further process it. So it is easy, or it is convenient to use a switch along with a capacitor. And this is a very basic sampling circuit with a switch and a simple switch and a capacitor. So this is your input voltage V in. Here I can mark it as V out, and this is the capacitor. So usually we call this capacitor as a hold capacitor, because this capacitor is responsible to sample the signal and hold the information for a cycle. Right, so we usually mark it as CH, hold capacitor, and this is the switch. Switch default, we know it should be controlled with the signal at the gate. Right. Now again, as we discussed before, one more thing. Yeah, no need. I am not repeating that. What I was telling is, if whenever I use a MOSFET as a switch here, one advantage of MOSFET over BJT is MOSFET can be turned on. MOSFET can be turned on while carrying a zero current. Right, because in order to turn on MOSFET, what we need is a sufficient gate to source voltage, and if you provide that higher than the threshold, MOSFET will be turned on, and there is no current flow from the control signal to the channel. Now the only current what we are interested is actually the control signal, the current between the source and drain terminals, right? Now, so this is one thing. Another thing is the source and drain voltages. This is what we already discussed. These source and drain voltages are not tied or not pinned to the gate voltage. So as we discussed just now, a gate voltage, or the signal at gate will not have the signal at gate will not interfere with the information which is being passed. All right. So this is a basic sampling circuit. Now what we'll do is, probably you would have heard in your digital VLSI design course also that whenever you work with a MOSFET as a switch, it can either take, like the terminal source and drain can be interchangeably used. That is what something we say, right? A MOSFET switch can conduct either in conduct in both directions by just by exchanging the role of its source and drain. That is what we usually say. So what we'll do now is we'll take some time to understand how the source and drain can exchange their roles, thereby it can allow current to flow in either direction, right? So for that, what I'm writing here is MOSFET in MOSFET, source and drain can exchange their roles. So do you agree to this point, whether source and drain, whether they can exchange their roles? It all depends on what is the potential, what potential you have applied, because in contrast with BJT, you know that your emitter and collector cannot be interchanged because even the doping level is different there. But in the case of MOSFET, that is not it's not like that. We have the option to do this, right? So we'll study this under two cases. So case one is, let me again, I'm just taking a simple circuit. Instead of a switch, I am replacing that with a MOSFET, and I'm taking a capacitor here. This is a switch, what I know, sorry, the sampling circuit, and I'm providing a clock signal to the gate. Right now, what I'll do now is I'll let me mark this as input and this as output. So at first, what I do is I'll consider that the input is tied to ground, or I would say Vin is equal to 0 initially. At the same time, I'll also assume an initial condition here. So what I have here is a hold capacitor. Now the initial condition, what I'm assuming here is there is some voltage across the capacitor, and that voltage I'm marking it as VDD, the maximum voltage what I can use in this circuit, right? Now, if this is a condition, on one end, there are two terminals, source and drain. I haven't marked which is source and which is drain, but now with the conditions assumed, I can clearly say that this terminal is the source terminal here because it is tied to ground, and the other terminal is the drain terminal because that is connected to capacitor, and capacitor I am assuming an initial voltage of VDD, right? So if this is a case, what I can say is, since the input is 0, so what I want to do here is I have a sampling circuit, or I have a switch. Basically, I have a switch and a capacitor. Across capacitor, there is some voltage. Now, what I want to pass here to the output, my input is tied to 0, so my output also should actually come down to 0. That means the voltage across the capacitor should now discharge. Now, what is the discharging path? The discharging path is actually through the MOSFET here. So if you look at this circuit, I'll draw that this is a discharging path. The current will be flowing in this form, this way from drain to source through the MOSFET when the MOSFET is turned on. Because when the clock signal is high, I can say that the MOSFET is on. If the MOSFET is on, it will carry some current depending on what region it is, right? So to make it a little more clear, what I will do here is I'll consider a signal here. So this is a clock signal. Clock is moving from 0 to VDD, and this is the pos edge. The positive edge is this one, right? This is the clock signal. Now, since I have assumed an initial condition here where the capacitor is holding a voltage of VDD, what I can say is before. So now the instant here, what I am looking at is T0. T0 is my instant. Now, before that, capacitor is holding a voltage, so I will mark that voltage here as VDD. So now what happens at the instant T0? At the instant T0, the clock signal is going high. That will definitely make the transistor on. The transistor is turning on. The voltage VDD at the drain or across the capacitor will start discharging, and it will discharge until it will discharge up to 0 volt, right? So So how will be the discharging waveform? We can say that the discharging waveform of a capacitor is something like this, and it will take quite a long time actually to discharge, and that depends on the time constant what is available, right? Now our interest is, let us look at these things. I hope you are listening to me. Can I get some response in the chat? I don't know. Is there any delay in my? All right. Okay. Yeah. So what we'll do now is at t equal to t0, that is the instant which I am considering. At that instant, what I'm going to do now is I am trying to understand what region the MOSFET is, whether the MOSFET is directly in linear region or it is in saturation region, or is there a transition happening to the MOSFET, right? So let me look at this first at at t equal to t0. Right. So before that, before looking at the region of operation, first we should ensure that the MOSFET, is there a possibility for MOSFET to turn on? Now, since you are giving a clock which is varying from 0 to VDD, since you are applying a VDD pulse here, I can very well say that the voltage VGS here is greater than or equal to threshold. That means the MOSFET is on. Now at t equal to t0, let me write the voltages. What is VGS? VGS is VG minus VS. At t equal to t0, that voltage is nothing but VDD minus 0, which is equal to VDD. Now what is VDS? S is again ground, so VDS is also VDD. Now the gate and drain are at same potential. For a MOSFET, if the gate and drain are at same potential, I can very well clearly say that the MOSFET is in saturation region. If MOSFET is in saturation region, I know what is the current I have. What is the current here? Half mu and Cox W by L into VGS minus VT the whole square, and VGS is, in this case, it is VDD. This is in saturation. Now the question is, when the clock turns high, or when the clock moves from 0 to VDD at time t0 instant, now the capacitor is holding a voltage of VDD, but now that voltage will start discharging. That means your drain voltage is now going to drop from VDD to a lower voltage, right? That means what is dropping here? I can say that as the output voltage Vout falls, right? As Vout falls, what will happen? VDS also reduces. VDS also will fall, and at some point, when your Vout, at some point, when the Vout becomes VDD minus VT. So can you tell me what is the switching point? Now the transistor is in saturation. So when can I say that the transistor will move into triode region or linear region? Now both drain and gate are at same potential. We also know that the gate can go one threshold higher than drain, right? So if your drain voltage is one threshold lower than, okay, I'll draw in this form here. So if you have a MOSFET, now the condition is both are at same potential, both are at VDD, right? Now the other voltage is going to reduce, your drain is going to reduce. That means your gate will be high, and gate is at high and drain will come down. So this difference can be maximum of one threshold. When it drops lesser than one threshold, what will happen? The transistor should, or the transistor will definitely move to the other region of operation, right? So when your Vout becomes VDD minus VT, I can say that M1, okay, I'll just mark this transistor as M1. This transistor moves to triode region. This transistor moves to triode region. Now the moment you say that the transistor is in triode region, I can write the drain current equation, which is equal to mu and Cox W by L into VGS minus VT into VDS minus VDS square by 2. This is the current equation, right? Now the Vout start falling. Vout has come down. It has fallen down VDD minus VT. The transistor moved into triode, but that doesn't mean that the discharging will stop. The device M1 continue to discharge. This will continue to discharge CH, the whole capacitor, until it reaches 0. It will continually discharge up to 0. Right. Now, now as the transistor moved into triode region, so we know that, or you would have heard this many times even from your third semester, that the moment you say that you are using MOSFET as a switch, the regions between what you are switching is between the cutoff region and between the triode region, right? So because we know that when you say a switch, what we are expecting is when the switch is on, right? So if I say this is a switch, when the switch is on, we expect 0 resistance, and the switch is off, we expect infinite resistance, right? So now we want to see what is the resistance offered by this switch when it is on and it is in triode region. Can you tell me what is the resistance of this on switch? Since we know that now the transistor's current equation we know, and we can also say that now the VDS is becoming very small, right? Because as the capacitor keep on discharging, the VDS voltage is becoming very small. In that case, if you neglect the VDS square term or VDS square by 2 term, I can write the on resistance of the switch. When the switch is on, the on resistance can be written as 1 by mu n Cox W by L into VGS minus VT, or this can be further written by substituting the VGS value with VDD. This is VDD minus VT, right? So this is the on resistance of this NMOS switch. Now, if you ask me about this on resistance of the switch, on the value of the switch, so because in the denominator, since you have the voltage that VDD minus VT is quite large, the on resistance will be very small. So maybe you can also evaluate this with the help of some simulations, right? So this is my case one. So what I did is I started with I started with the initial value across the capacitor, and when at the switching instant it started discharging and it will come down to 0, and we also saw that the transistor is switching from saturation to triode region, and it is in triode region or in deep triode region until the charge across the capacitor is fully discharged, right? All right. So let it be there. Now let us move to the another case. So the initial starting point is what I was telling is in the case of MOSFET, the source and drain can exchange their roles, and these two cases are basically to explain that this exchange is possible, right? Now now I'm taking another case. I hope the first case what I explained was pretty clear. If not, please ping in the chat. Voltage at V in. Okay, there is a question. What is the voltage at V in when V out tends to 0? You're asking with respect to this, right? Yeah. If the question is with respect to the previous diagram in the case 1, so you can look at the graph what I have drawn here. What is this graph? This graph is basically your V out. What you're seeing here is, let me mark it as V out. Your V out is keep on discharging, and your input side is actually shorted to ground. So that means the input voltage is basically 0. That is why the capacitor is discharging, right? The input voltage what I have is 0. So your V out is actually discharging, and eventually or finally after the switching transient, V out also will come to 0. Now when it will come to 0, the time, it depends on the time constant of this switch, RC switch. I don't know whether I understood your question rightly, Ankit. Yeah, if you're clear, I hope you understood that. Still, if you have questions, we can definitely discuss at the end of the class. All right. Now we'll also look at another case because in the previous case we were looking at some initial condition with respect to the capacitor. So now I'll not do that. Rather, what I'll do is I'll take this capacitor here. So this is V in, this is V out, this is the clock. Now I'm connecting a 1 volt. Say I'm connecting a 1 volt signal to the to one side, to the input side, and capacitor, this whole capacitor, there is no voltage across, or I'll say that initially the capacitor is relaxed and the voltage, the initial voltage across the capacitor is 0. Right. Now, if this is a case, by looking at the voltages available, I can clearly say that since the capacitance or the since the voltage across the capacitor is 0, this can be identified as a source. This can be identified as drain. This being the gate terminal. Right. Now, look at the voltage. Okay, let me look at let me see. Let us see how which region it is. So as before, I am just drawing the clock signal here. This is clock, this is 0 and VDD, and initially the voltage across the capacitor is 0. So if I mark it here, at switching instant T0, the voltage output is 0. Right. Now, if I look at input voltage, what I am taking is input voltage is plus 1 volt. Now, output at T equal to T0 is equal to 0 volt. Right. Output is 0. Now, what is VDD? When I say VDD, previously I was mentioning it as a clock. Say in this case, I'll just take this VDD as some 3 volt, just to explain one case here. Now, if this is a situation, if I want to know what is the region of operation of the device, I should write what is VDS and VGS. So what is VDS here? VDS is S is 0, D is at 1, so VDS is 1 volt, VG is at 3, VS is at 0, so VGS is 3 volt. So directly I can say your VDS is much lesser than VGS minus VT, assuming a threshold of 1 volt or so in this case. Therefore, we can clearly say the drain source region, and also we can say under this condition, MOSFET, the transistor M1, is in triode region. This is in triode region. Right. Now, what will happen? The MOSFET will continue in triode region because the input side, what you have is 1 volt, and what will happen? The MOSFET will start charging. So it's in the triode region. So maybe you can also think of this as a resistance here with some on resistance value. We'll see what is the on resistance value, and the current flow will be in this direction. This is the current flow direction, and we can clearly say that the current is triode region current. And what will happen? The output, the capacitor will keep on charging, and it will actually eventually reach the voltage of 1. Right. So again, that will take some time depending on the time constant, right? So what I can say is M1 is in triode region. M1 will continue in triode region itself until V out becomes 1 volt. And I can say that V out will be approximately 1 in a very short time, but it will take longer time actually to reach that voltage. Now, if you write the current equation here, sorry, not current equation, the on resistance of the switch in comparison with the previous one, the equation remains same, 1 by mu n Cox W by L into VGS minus VT. Right, this is the previous, this is same as the previous equation. But if you look at the VG and VS voltage, I can write in this little more detail as VG is VDD. What is VS? Now VS is the output, right? So I can write, so output will eventually, the output voltage will be same as your input voltage. So I will write it as VD minus V in minus VT. So why I have written it as V in is because when the switch is on, the MOSFET is in triode region. It will offer a resistance on resistance, and finally the output will be equal to input. with a small difference, right? So this is the on resistance, mu and Cox W by L into VDD minus Vn minus Vt, right? So if you take these two examples, the case 1 and case 2, we clearly saw that depending on the voltage or the concluding remarks, I'll just write the concluding points here. So what are the takeaway points here? One is MOS switch can conduct current in either direction. That is just by exchanging the role of source and drain. So what I meant by telling that exchanging the role of source and drain is basically whenever you have a higher voltage, that terminal will be a drain, and when you have a low voltage, that terminal will be naturally source. That is one thing. The second thing is, so when the switch is on, when the MOSFET switch is on, the output V out will follow V in. Yeah. So when switch is on, V out follows V in, and when switch is off, the voltage at V out or V out remains constant. Why it remains constant? Because the arrangement is in such a way that MOSFET will offer an infinite resistance ideally, and it will not have any discharging path for the capacitor to discharge, right? So in conclusion, what I can say is the circuit, so whatever you have as a sampling circuit, that circuit will track the signal when the clock is high, and it'll freeze the instantaneous value of the input voltage across the capacitor as soon as the clock goes low, right? So it is not as simple as how I told. We'll in the first unit itself, we'll see the variance of the sampling circuit. We will call as sampling circuit or track and hold circuit, where depending on the clock signal, how the input is getting tracked at the output. So that we will see shortly in the coming lectures. All right. So these are two things what I want to mention. I just want to give a simple example here. With that, we'll wind up today's class. So what I have is a switch, sampling switch, and a capacitor CH. You can assume that this capacitor is 1 picofarad, but anyway, for this numerical, we are not going to do something with the value of the capacitance. You can also consider that your gate is connected to a clock which is of 3 volt, and at the input side you have a 100 megahertz signal, 10 megahertz signal, of this, a sine wave, and it is also given that the maximum amplitude is 0.5. This is 0.5. Yeah. So naturally, since it is a sampling circuit, the expected output is a sampled output. So I'm not going to give you the clock frequency, because we are not going to do anything with that. The only intention is to calculate the on resistance in this case. So our output also will it will be a sampled output. I'm just drawing it as it is. Output also can come maximum only up to 0.5, right? So what you can do is, you can just calculate the minimum and maximum resistance, the minimum and maximum on resistance of the MOSFET. I just mark it as M1. Now to do the calculation, you can assume the value of mu and Cox as 50 microamps per volt square, W by L as 5, and the threshold voltage as 0.7. And take these values and you can find the minimum and maximum on resistance. Then you will also observe that the on resistance of a MOSFET is whenever you have an NMOS switch. Here you will observe that the on resistance of the MOSFET depends on the signal, input signal, which is actually a potential problem, and we'll see how we can avoid that, right? So what I'll do is I'll just wind up here. I would request you to just solve this question and be ready with the answers for the next day. All right, so thank you so much. Please wait online. I have a few more instructions to give.